Now we're going to look at chemical equations. And chemical equations are a critical part of the language in chemistry. These are written shorthand ways of describing reactions, and they give critical information about the reactions. They tell us the formula of the reactants. These are the chemicals that actually react together, as well as the formulas of the products. These are the chemicals that are produced, the new chemicals that are produced in a chemical reaction. A chemical equation also tells us the state of reactants and products. It tells us the relative number of reactant and product molecules that are required for a given reaction. And this piece here can be used to determine masses of reactants used and products that can be made. So for example, we can liken this to making a cake. You need to know exactly the exact amount of your ingredients, and you need to know how much you're going to make. Chemistry is very much like cooking in that respect, and we get that type of information from our chemical equations. Now, a key component of chemical equations is the law of conservation of mass. According to this law, matter cannot be created nor destroyed, just changes form. Therefore, the total mass cannot change. Now, this right here is actually a little bit of a lie, but you won't know the real truth until you take Chem 152. So for right now, we're going to assume it is the truth. We're going to act as if it is the truth. So the total mass of the reactants will be the same as the total mass of the products. We can use this for all of our work in this class. In a chemical reaction, all the atoms present at the beginning are still present at the end. They're just arranged differently. And if all the atoms are still there, then the mass will not change. So we're going to use a simple chemical reaction, the combustion of methane, to investigate chemical reactions, in particular chemical equation. So let's look at this statement here. Methane gas burns to produce carbon dioxide gas and gaseous water. From this statement, we can actually write a chemical equation. We just need to remember that whenever something burns, it is reacting with oxygen. And we also want to remember that oxygen is a diatomic element that exists as a gas at ambient conditions. So here's the statement again. We remember that when something burns, it reacts with O2. We also need to know the formula of methane. Here it is. Methane is 1 carbon, 4 hydrogen. It is natural gas, so it's always in the gaseous state at room temperature. It is reacting with oxygen. When two chemicals are reacting, they are separated by this plus sign. This plus sign is very important. If it's not here, then the two chemicals may look as they're actually one chemical. Here we have their states, and then this arrow indicates produces or forms. This arrow indicates that some change is going to occur. And on the other side of the arrow, we have our products. These are the reactants, the chemicals that react, and here are the products, the chemicals that are produced. So here it tells us in this reaction, carbon dioxide gas and gaseous water are produced. So here's the formula for carbon dioxide. We write its state, and water. And again, any chemicals are going to be separated by this positive sign. That allows any confusion that could occur from these chemicals being too close to be avoided. So how do we read this equation? As it stands now, this says 1 molecule of methane gas combines with or reacts with 1 molecule of oxygen gas to make or to produce 1 molecule of carbon dioxide gas and 1 molecule of water gas. Well, we read it correctly. However, if we remember our conservation of mass, this equation is not correct. And let's look at counting our atoms, and we'll see why it's not. If we look on our reactant side, we have 1 atom of carbon from our molecule of methane, 4 hydrogen atoms, and 2 oxygen atoms from our molecule of oxygen. On our product side, we have 1 atom of carbon from our carbon dioxide molecule, 2 oxygen atoms, and 1 oxygen atom to combine to make 3 oxygen atoms, and 2 hydrogen atoms. So if we look at the total number of carbon, hydrogen, and oxygen, it's not the same as it is on this side. So that violates the law of conservation of matter, and what we're going to do is we're going to do what's known as balance the equation to make sure it doesn't violate this law of conservation of matter. We need the same number of atoms on both sides of the equation, the reactant side and the product side. So here's a pictorial representation. It's a little easier to see since it's color-coded. Here we have 2 oxygen atoms. Here we have 3 oxygen atoms. Here we have 4 hydrogen atoms. Here we only have 2. So it's clearly not balanced, and that violates, as I said, the law of conservation of mass. So we've got to get it so we have the same number of atoms of each element on both sides of the arrow. To balance equations, what we are allowed to do is we are allowed to change the actual number of molecules. And the way that we indicate or change that is by changing the number in front of each chemical. This is what's known as a coefficient. In our previous example, we just had 1 molecule of everything. But now I have 2 molecules of oxygen and 2 molecules of water. I am allowed to change the number of any molecule I need to get it balanced. And if we look at the number of atoms on each side, they are now equivalent. 1 carbon atom, 4 hydrogen atoms, 4 oxygen atoms. On my product side, 1 carbon atom, 2 times 2 is 4 hydrogen, and 2 times 1 is 2, plus 2 is 4 oxygen. And I failed to mention I got this 4 oxygen here by multiplying 2 by 2. So to count the number of atoms, you take this number in front, which is known as a coefficient, and you multiply it by the subscript. That gives you the total number. If you have an element that is in more than 1 compound, like oxygen, you multiply the coefficient by the subscript and then add the 2 values together. If nothing is specifically written, then your coefficient is 1. So 1 times 2 gives me 2 oxygens from carbon dioxide, and 2 times 1 gives me 2 oxygens from 2 molecules of water. So here's another pictorial representation, and I can see when I have 2 molecules of oxygen, now I have balanced my oxygens. And when I have 2 molecules of water, my oxygens and my hydrogens are balanced. So when I change this number in front, I change the actual number of molecules, which I'm allowed to do. I can add as many as I need to get a balanced equation. What we cannot change are the subscripts. If we change the subscripts, we're actually changing the chemical, which is completely illegal. The only thing that we can change are the coefficients. So let's review some of the vocab. Here's our balanced equation. The chemicals in blue on the left of the arrow are the reactants. The chemicals in purple on the right are the products. This tells us our state. The number in front tells us the number of molecules. This is known as the coefficient. And these lowercase numbers, part of the formula, are known as subscripts. The subscripts are not changeable, but the coefficients are.